So this is what these two graphs look like, the function and its inverse function. Okay, we're going to talk about logarithms now. Now logarithms are a lot like exponents. They're the inverse function of an exponent. So just like, remember this, that for exponential functions, okay, let's write an exponential function a to the x. Remember that the domain was all real numbers, and that the range of the basic, if you don't shift it up or down, the range is 0 to infinity. Well, for logarithmic functions, it's just the opposite. Your domain is 0 to infinity, and your range is, the symbol copied a little weird here, is negative infinity to positive infinity. That's how, so, and does that make sense? Inverse function, remember how I said you kind of swap the domain and the range? Well, that's what we're doing here. So you still have that base of a. This is log with a base of a. That's the inverse function of the exponential y equals a to the x. And we'll go over some of the rules there, and we'll talk about how to use these in your calculator and what the logs in your calculator are. Now, log in your calculator, the log, that's actually the base 10 log, okay? And then the len, that's the base e log. So anytime you type that len button, that's actually log base. Remember, e was like 2.718, etc. And so it's log base that of x. When you hit just the log button, that's log base 10 of whatever number you put after that. Sometimes it'll open little parentheses here, but those are the numbers that your calculators are using there. So the log base e is len, and the log button that doesn't show up a base in your calculator. It says log and then kind of opens parentheses. That's the log base 10. It's also called the common logarithm. And by the way, ln is like log natural. It's natural log. That's why it's ln. That's why we use those abbreviations there. When we're talking about our inverse properties for logs, so we have a few properties in logs. For your base of a, a to the log a of x is equal to x. You might not be as familiar with that as you are with this one. E to the natural log of x is equal to x. Remember, if we're trying to like cancel out an e, like len and e to the x are inverse functions of each other. We did practice some of these since we kind of cheated ahead when we were solving for when we tried to solve for x in our exponential functions. We tried to solve for our exponent. We actually used logs and did it by hand. So some of this is going to be familiar to us. The product rules and quotient rules work sort of similar to how they do in exponents. You're not going to recognize them as easily because logs are just not as familiar as you haven't been doing logs as long as you've been doing exponents. But if you have the log of a base of something, x times y, that's going to be equal to log of that base a, x plus log of that base, whatever it is, y. The quotient rule is, all right, if you have log of a base, okay, and then it's x divided by y, if it's written like this, well, just like multiplication, if you multiply exponents, don't we add the powers? If you divide the exponents, you subtract the power. So, you're kind of subtracting the logs here. So it's a log base a of x, and that's log base a of y, and it's the difference of those. There's also the power rule, which we use when we were solving those functions in 1.3. So log of x to the y. Remember we said you take this rule, you can kind of take that y and like slingshot it in front. So it's going to look like this. That's going to be equal to that power on the this number here is going to become like the new coefficient in front of your log function. Those are the most important rules you want to be familiar with. Okay, so if we want to solve this, remember we did some of these in a section previous. I want to get x by itself. What I'm going to do is I'm going to choose to use len. All right, I don't need to worry about using log base 2 or anything. I'm going to use len of both sides. You can use log of both sides. They're interchangeable because the rules apply. It doesn't matter what base you use. I'm going to do len of 12 over here, and I'm applying that third rule right here where you kind of move the power in front because I want to get the x out of the air here. So that's x natural log of 2 is equal to natural log of 12, And so I'm going to divide by ln 2 on both sides. So x is equal to ln 12 over natural log of 2. And I can find out exactly an approximation of what that value is in my calculator. But this is exactly what x would be here. If I want to solve for this, let's see. E to the x plus 5 equals 60. Well, that's... logically, I'd subtract 5 on both sides. So e to the x is equal to 55. So I'm going to take the natural log. Here, I'm definitely going to want to use natural log of both sides. Is equal to natural log of 55. And these are inverse functions of each other. So instead of... I could just kind of shortcut it and like kind of cancel these out like that and picture the x just dropping. But since it looks a little weird, I'm going to rewrite it. X natural log of e equals natural log of 55. And what's going to happen is, these will cancel each other out right here. If you do this in your calculator, you'll notice that when I say they cancel each other out, if you do natural log of e, you're going to get 1. So you can test that. Go and test on your calculator. Natural log of e is equal to 1. Because what it is, it's log base e of e equals, some value here. Well, it's like log base e of e to the x. What power, what would x be? What power do I raise e to get e? Well, you raise it to the first power. That's how that works. Okay. Sometimes we'll have to do change of base operations. If you ever need to do that, here's how it works. Log base a of x is equal to the natural log of x over the natural log of a. That's the relationship we're always going to use there. So if ever you want to evaluate log for some base and obtain its graph, you can switch the you can use this to change the bases there. All right, here we're going to look at this graph. We want to find the domain. So log base 2 of x plus 2. I can't really do this in my calculator, right? We don't have like a log base 2 button. We have the log base 10. We have the log base e. So what I can do is I can do a change of base operation. So remember, this is the formula here at log base a of x equals natural log of a over natural log of x over natural log of a. So I'm going to do, I know that the log base 2 of x, that's equal to natural log here. 2 is my a, so it's natural log of x over natural log of 2. So this value right here, that's this part right here, right? I'm going to replace with this ln of x over ln of 2. So it's y is equal to natural log of x over natural log of 2. And it's whatever that graph is, shift it up. And I'm just going to go ahead and enter this in my calculator. So if I graph this in my calculator, I'm graphing this function, which, again, I don't have a log base 2 button, so I just do log of x over whatever this base was, and that's the equivalent of this original graph here. Put that into my calculator, hit graph, and if you want, you can do the Z box. It's one of my favorite things. If you want to really see how that thing differs from regular natural log, we can go and kind of zoom in on this graph a little bit. All natural log functions, assuming they're not shifted to the left and the right, they're going to kind of hug the y-axis, which makes sense because they're the inverse functions of exponential functions. Exponential function didn't exponential functions hug the x-axis, like as you go to the left? So natural log functions are all going to hug the y-axis, and instead of as you go to the left, it's as you go down. So as you get to the negative y values, as you go map to negative y values, it's going to hug the x-axis. In the same way that exponential functions hugged the, as you went negative x values, it hugged the x-axis there. Now, we did one similar to this, again on exponential functions. We're officially covering it here. So this is sort of a review from the other section. We want to find out at what value, at what time value are we going to hit this population? So see if you can pick apart what's going on here. Remember our our PERT formula. So be careful. This P actually represents population. So I'm gonna, instead of putting a P, I'm gonna do population. I'm gonna write my P e to the RT because that's what we're used to seeing. Right. See how this 105, 105,000. That's gonna be our initial population. And this is we're doing on a continuous model. What percentage does the population increase? Think about that. Remember, the R is just the actual R, so if you want to find the percentage, you can move the decimal two places on the right. So that's going to be a 1.5% population growth, and the T represents time here. So if we have this population growth here, so I'm going to, this is the model of my population. Again, this P is not initial population, it's the variable they use for population. 105,300 times e to the 0.015 t. All right, and 0 represents 1990 here. But we want to know when our population is going to be equal to, when we're going to hit 150,000. So just like we did last time, we're going to divide on the initial population on both sides. 105,300. To make my life a little easier to not copy down 0 so much, I'm going to cancel out 2 of those zeros. Then I'm going to just record that value. Have 1500 over, this could be 1053. Okay, that's equal to e to the 0.015 t. I'm going to use natural log, and that's actually saving me a few steps. Natural log is the inverse function of e. So what will happen here is I've got natural log of this side equals natural log of all this stuff. Remember that the t kind of swings out in front. So you're going to end up getting t times natural log of e. I'm sorry, the whole exponent is 0.015. So that whole thing swings in front, 0.015 t. And natural log of e, again, you can confirm that in your calculator. Natural log of e is just 1. And if you do e to the natural log of 1, for instance, you're going to get 1, the same thing. This is natural log of e to the 1 power, if you want to see it that way. But natural log of e is 1. So what we get is natural log of 1500 over 1053 is equal to 0.015 t. So if I want to solve for t, I'm going to take 0.015, divide that on both sides, so 0.015 here, and that's going to be what value of t I get. So whatever value I solve for t, I'm going to take it and add that to 1990 to get the year, because remember, a t of 0 would be 1990, a t equal to 1 would be 1991, a t equal to 8 would be 1998. So I'm going to find out what that value is on my calculator. So here I put that value, what I solved that t is actually going to be equal to. But then in my calculator I got 23, and again, 0 represents 1990, so I'm going to add 1,990 to this. So assuming a 1.5% population growth, and you start off with only 105,000, it makes sense that it would take you, 23 and a half years to get to 150,000, which is, 50% more than what you had up to. So that would happen. They would hit that population, assuming you stayed growing at this rate in 2013. Now, I went ahead and decided to do this graphically too, and I'll show you how much trouble it is to do it graphically. I put this function, which took a while to enter. Then I had the foreknowledge of going, okay, I want to know when this thing is equal to 150,000. I wouldn't normally be able to see it on a graph. If I go to zoom standard, I wouldn't be able to see that graph, but I had to know already that I wanted to go at least as far out as 23 years, right? And that's where 23 is. And I also have to know that I want to hit 150,000. So doing this graphically is a lot more work. It's really easy since we can do it this algebraic way using logarithms.
That's the end of this part of the lecture. Yeah!
The views and opinions expressed in this video are solely those of Mr. Vogel and do not necessarily reflect those of the School of Sacred Heart, Agricultural Board of Directors, Administration of the United States Schools, or anyone else. Visit our website at shhcoto.org.